In this video, we'll go over the basics of the Hopfield network. Let's take a look at how information is stored and retrieved in a Hopfield network. This video was produced in Korean and then translated into English. The audio was generated by AI, text-to-speech. In this video, we will look at the basic structure of the Hopfield network. And let's learn how to store and retrieve image patterns through a simple example. Finally, let's implement this in code. Hopfield network was first introduced by John Hopfield in his 1982 paper. This is a neural network model that aims to emulate and understand the mechanisms of our memory that the brain performs when storing and recalling information. Hopfield network can be used for associative memory and content addressable memory. Physicist Hopfield noted the following in his paper. Computational properties of use to biological organisms or to the construction of computers can emerge as collective properties of systems, having a large number of simple equivalent components or neurons. The physical meaning of content addressable memory is described by an appropriate phase space flow of the state of a system. The collective properties of this model produce a content addressable memory that can retrieve an entire memory from any partial memory. Now let's look at the basic structure of the Hopfield network. We have the following n input patterns. Each pattern consists of 5 states. We want to store these input patterns in a Hopfield network. The structure of a simple Hopfield network is as follows. The number of neurons is m, which is the number of states in the input pattern. In this example, m is 5. Neurons are fully interconnected, and each connection is bidirectional. Each neuron has 2 states, 0 or 1. State 0 means the neuron is not firing. And state 1 means the neuron is firing at maximum rate. The connection weights of a Hopfield network are computed as follows. N is the number of data points to be stored in this network. 2s minus 1 is to convert the binary state of a neuron into a bipolar state. This is the Hebbian learning rule that we looked at in the previous video. Neurons that have simultaneously similar activities have their synaptic strengths increase. And neurons that have simultaneously dissimilar activities have their synaptic strengths decrease. This is equation 2 in the paper. Each neuron has no self-feedback, i.e. no connection to itself. And the connection weights between neurons are symmetrical. The weights is an m by m matrix. And this is a symmetric matrix with a 0 diagonal. The input data points are stored in this weight matrix. That is, this is the associative memory. Next, let's look at the process of retrieving information stored in this memory. We want to retrieve an entire memory item stored in this network on the basis of sufficient partial information. It's like reconstructing a dinosaur from a few bones. Let's say this is partial information, a test data point that is fed into the network. We want to update each state in this data point using the weight matrix on the left, built with the training data. Then we can get a complete memory of this partial memory. First, we use this formula to compute the activation value of each neuron. For example, let's compute the activation value of this neuron. The activation value of neuron 1 is computed as follows. This subnetwork is equivalent to a feed-forward network, where neuron 1 is the output layer and the rest of the neurons are the input layer. If this activation value is greater than U1, the threshold of neuron 1, the state of neuron 1, is updated to 1. That is, neuron 1 fires. Otherwise, the state of the neuron 1 is updated to 0. The threshold U can be thought of as the bias of each neuron. It is assumed to be 0 here. In this way, the state of each neuron is updated. This process is repeated until the state of each neuron no longer changes, that is, until it converges to a stable state. Then we can get a new state vector for this test data point. This is the complete information retrieved from memory based on partial information. We need to update the neurons in random order. This increases the likelihood of convergence to a stable state. Otherwise, the network may oscillate. Next, let's look at the process of storing and recalling image patterns in a Hopfield network through a simple example. We want to store the following 2 input patterns in a Hopfield network. Since each input vector has 5 elements, we build a network with 5 neurons like this. We use this formula to find the weight matrix. Converting the binary state of each input pattern to a bipolar state gives the following result. 1 becomes positive 1 as it is, and 0 is converted to negative 1. We compute the matrix product of bipolar states in this way. Then we set the diagonal elements to 0. We can then obtain the following weight matrix. This is a symmetric matrix with a 0 diagonal. The 2 input patterns are stored in this matrix. Now we have a matrix storing the 2 input patterns. Next, let's look at the process of retrieving image patterns from a Hopfield network. Let's update each state of the test pattern ST using the weight matrix of this network. This test pattern is a partial pattern where the last state of the first input pattern is corrupted. Let's update the state of each neuron in this random order. First, we update the state of neuron 1. Then I is 1 and J is 2, 3, 4, 5. We use this formula to compute the output of this subnetwork as follows. The output is -2. Since this is less than 0, S1 is updated to 0. Next, we update the state of neuron 3. This time I is 3 and J is 1, 2, 4, 5. We compute the output of this subnetwork as follows. The output is also -2. Since this is also less than 0, S3 is updated to 0. In this way, we update the state of the remaining neurons. Then we get the following output pattern. This is identical to the first input pattern. That is, the corrupted pattern is reconstructed into the original pattern. Finally, let's implement the process of storing and recalling memories in code. The input patterns are as follows. Each pattern consists of 9 elements. Therefore, the number of neurons in the Hopfield network is also 9. And the weight matrix will have 9 rows and 9 columns. N is 2, the number of input patterns, and M is 9, the number of neurons. The first pattern is an image of the letter T. The second pattern is an image of the letter U. We use this formula to find the weight matrix. The test patterns are as follows. The first pattern is an image of a corrupted T, and the second pattern is an image of a corrupted U. Load the test patterns one by one and update each state. Randomly select M neurons and use this formula to calculate the output values of the selected neurons one by one. If the output value is greater than 0, the state of the neuron is updated to 1. If the output value is 0, the state of the neuron is not updated and the previous state is maintained. If the output value is less than 0, the neuron state is updated to 0. Repeat this process 10 times. Let's check the results. The weight matrix is as follows. The corrupted patterns were successfully reconstructed into their original patterns as follows. A Hopfield network can store up to about 0.15 meters memories. In this case, since M is 9, only up to 2 patterns can be stored. If you input 3 patterns into this network, the reconstruction will fail. We will return to this issue later. Let's run this code. We got the following results. In this video, we look at the basic operation of a Hopfield network. In the next video, we'll look at the energy function of a Hopfield network.